We're going to be reviewing some sample problems to help you prep for the AP exam, and we're going to focus on probability and random variables. So in front of you, I have a screenshot of your formula sheet for the AP Stat exam. So part 2 has a lot of the probability formulas that you're going to be using. So the union of two sets, it's reminding you that you need to subtract the intersection. You can only just add if we know for a fact that we have disjoint events. So in general, we subtract. This is the probability of A, given that B has already occurred, is equal to the intersection of two sets divided by the probability of just B. This formula comes in handy a lot when you're asked to prove independence. We're going to go through one of those problems. That was always an area of struggle. Pointing these out, I don't believe I have any random variable questions in the first 6 we're going to do in this video, but we may visit the binomial or geometric distribution. And one of the things that if you're ever asked to compute with a binomial distribution, you always got to make sure you state your parameters. And I think a lot of times you all forget that, but if you just glance at your formula sheet, if you list your parameters N and P, you're going to get full credit. Got your formula here, the mean and the standard deviation. All right, let's go into some problems. So we're specifically going to look at the first 6 in the packet that I've given you. So we're going to begin with some general formulas here, good old basics. So suppose the probability of A is 0.35, B is 0.66, and their intersection is 0.27. You might want to quickly draw a Venn diagram to help you answer these questions, but I think we can pretty much go straight with some formulas. So the probability of the complement of A. So if A is 0.35, the complement would be 1 minus, that's a really big stylus, hold on. It would be 1 minus 0.35 or 0.65. Okay, the probability of the union of A and B. Well, that's where we've got to subtract any overlap. So just using the general formula would be add the two together and subtract their intersection. So we are going to do 0.35 plus 0.6 and then subtract the 0.27, and that gives me 0.68. And I hope you are certainly doing these with me. Pause the video. I'm going fast for obviously the sake of time, but hit pause when you need to catch up or get ahead of me and just use my instruction to check your answer. Okay, so the probability of A given B is equal to the probability of the intersection of your two events divided by the probability of B. This formula is on your sheet. So we're given that that's 0.27 divided by 0.6. On my calculator, that gives me 0.45. Now, are these independent? All right, big concept. This is going to come up somewhere on your exam. If our events are independent, that means that one is not like influencing the other. It's not affecting it in any way. So the probability of A has to be equal to the probability of A given that B has already occurred. Right? So if these two values are equal to each other, then we conclude that we have independence. Well, the probability of A is equal to 0.35. We just computed probability of A given B right here in part C. Okay, we use this formula. It's equal to 0.45. So probability of A given B is 0.45. Since these are not equal, sorry, let me zoom out here. Since these are not equal, these are not independent. All right, keep moving. Example 1, suppose the probability that a construction company will be awarded a certain contract is 0.25. The probability that it will be awarded a second contract is 0.21, and the probability that it will get both contracts is 0.13. What is the probability that the company will win at least one of the contracts? Okay, so I'm a visual learner, so I make a picture. So the one contract I'll just say is contract A is 0.25. Actually, you know what? I start in the middle. Okay, so I'm going to say it's 0.13 for both to happen. And I'm told that it's 0.25 for the one, so that means 0.12, because it's got to add to 0.25, is here. And the second one is 0.21, so this would be 0.08 over here. And what is the probability that the company will win at least one of the two? Well, at least one of the two would be all of this added together. So they could get this one or both. So adding it all together would be 0.33. Okay, then we're given a two-way table in example 2. A researcher interested in eye color versus success in a math program collected the following data from a random sample of 2,000 high school students. Okay, if you're not given your totals, you would want to do that, but we're given our totals and adds to 2,000 here. So I'm going to be asked several questions from this. What is the probability that a student from this group fails the math program? So fails is a total of 200 out of 2,000 is going to be 1/10 or 0.10. In B, what is the probability that a student from this group fails the math? So fails given, so put that vertical line, that he or she has blue eyes. So some students like to think of this logically. You can also use your formula. So fails given that they're blue, well, there's 10 fail out of 100. So again, 10 out of 100, or that would be 1/10, 10%. You could also use your formula, probability of the intersection, meaning fails and blue divided by the probability of just blue. Okay, so that logic will also give you the same values. So here's your intersection of the total probability of blue, so 10 out of 100. Okay, and then are blue eyes and failing the math program independent or dependent? So in order to have independence, this is where again we say the probability of failing has to be equal to the probability of failing given that you have blue eyes. Okay? Well, we just found those two probabilities in part A and B. Because they are equal to each other, then yes, we have independence here. Okay, example 3. Of the 60 teenagers in a recent study, 15 had type 2 diabetes, 20 had high blood pressure, and 10 had both. Suppose one of the 60 obese teenagers is randomly selected. Okay, so again, I'm a visual learner. You could probably do a two-way table. I'm going with a Venn diagram. It's just usually my method of choice. Type 2 versus, I'll say, high blood pressure. And we had 10 with both. I start in the middle. Total of 15 with type 2, so that's 5 here. Total of 20 with high blood pressure, so that's 10 here. We have a total of 60 teenagers. So 25 have one of these or both conditions, so that leaves 35 who are, I guess we could say, healthy. All right, so given that the teenager has type 2 diabetes, what is the probability that he or she also has high blood pressure? So it's saying the probability, what's the probability that is high blood pressure given that they have type 2 diabetes? Okay, so I'm using some shorthanded notation. So that's equal to the probability, using your formula from your formula sheet, probability of the intersection of the two, divided by the probability of the second one, so type 2. Okay, so if I just find these raw counts, my raw counts would be, let's see, 10 is the intersection out of 15, and if I change that to decimal, it's approximately 0.667. Okay, part B, if the teenager does not have high blood pressure, what is the probability that he or she also does not have type 2 diabetes? So this would be equal to the intersection of the two. Okay, so the intersection of the two would be those who do not have type 2 and do not have high blood pressure. So that's your healthy people. That's the 35. Out of probability of those who do not have high blood pressure. Okay, so high blood pressure complement, in other words, on the bottom. So 20 in here have high blood pressure, so the complement would be 5 plus 35 or 40. So you can change that to a decimal. Going on to 4. The probability that Michael misses a free throw shot is 0.1. If he goes to the line to shoot 3 free throws due to a foul on a 3-point shot, part A, what is the probability that Michael misses all 3 shots? What assumptions did you make in order to calculate this probability? So missing all 3, well, 0.1 on the first, 0.1 on the second, 0.1 on the third is 0.001. Now, what assumption did I make in order to do that? I'm assuming that his shots are independent. In order to be able to multiply, I'm assuming that, what happens on the first is not affecting the second, which may be a bit of a leap, in a basketball game. Part B, what is the probability that Michael makes at least one of these 3 shots? So the probability of making at least one is probability of making greater than or equal to 1. I'm going to say that's equal to the complement of making none. Or I guess I could say missing all 3. Well, we just found the probability of missing all 3. So it would be 1 minus the 0.001 or 0.999. There are other ways to do that one. That's just how my brain thinks it through. Part C, what's the probability that Michael makes the first but not the second or the third? So makes the first would be 0.9, and then missing times 0.1 times 0.1, that's going to be 0.009. All right. Example 5. Of the 10,000 freshmen at the University of Texas, 7,000 must take English, 6,000 must take history, and 5,000 both. Okay, so set up a Venn diagram, pause the video, and check it. Okay, part A, what's the probability that the selected student must take English? So that's going to be 7,000 out of your 10,000, which is 7/10. What is the probability that the selected student must take both English and history? So that's going to be 5,000 out of 10,000 or a half, 0.5. Suppose that you learn that the selected student must take English. What is the probability that this student must take both English and history? So that's really saying probability of both, given that they are taking English. So that's your intersection of the two. So that's 5,000 divided by probability of just taking English. So we got 7,000 just taking English. So this is 5/7 or 0.71428 approximately. All right. Are the outcomes must take English and must take history independent? So in order to answer this, this is saying the probability that you take English has to be equal to, this is now the 3rd time I'm addressing independence in this video alone. So English given that they take history. So probability that they take English, we did that already. That is 0.7 right here, this part. Now, the probability of English, this right here, given that they take history, that's equal to the probability of the intersection of the two, so English with history, given that they, over the probability of history, excuse me. All right, so the intersection of the two, Raw counts is 5,000 students divided by 6,000. So that's 5/6, which is not equal to 0.7. So probability of English equals 0.7. I'm going to say that does not equal, and I'll just switch colors here, the probability of English given history, which equaled 5/6, whatever that is as a decimal. I think that's 0.83. Double check that on your calculator, but definitely not equal. Okay. Now part E says, so answer the question posed in part D. All right, so revisit this. If only 4,200 of the students must take both English and history. So my understanding of that is it's saying just change this intersection part to 4,200, in other words. Okay, so if we were saying forget that, let's now say it's 4,200. How does that alter things? So if there, I don't think I need to adjust everything else in the table or in the Venn diagram. I think we can still just answer the questions because the probability of English is not going to change. Okay, so does the probability of English equal the probability of English given history? Okay, so probability of English is still 0.7. Probability of English given history is going to change, right? This is what we just did over here, okay? The 5,000 over 6,000. So if we change that top number, in other words, to 4,200 divided by probability those taking history, well, that's still a grand total of 6,000, even though we would have to adjust those just taking history. And we reduce that, let's see, that does reduce to 0.7, okay? So we would get that they're equal, and then therefore they are independent. So I don't know if I ever stated my conclusion on the top one. It was no. All right, number 6, last one I'm going to talk about in this video. 2 office assistants at Penny Lane High School are responsible for getting the daily tardy list to the appropriate principals by 3:00 p.m. daily. Rudy works on lists 30% of the days, and Fawn works on the tardy list 70% of the days. Rudy fails to get the list to the correct principals in time 10% of the time, which would make him tardy with tardy lists. Fawn, not much better, manages to get the tardy list to the correct principals 92% of the time. Let's say that you are principal and the tardy list is late. What is the probability that today Rudy is responsible for the list? All right, so I'm going with a tree diagram. I'm given multiple percents and different things are happening. All right, so we got 2 secretaries or office assistants, Rudy and Fawn. Rudy does the list 30% of the time, so Fawn would do it 70% of the time. And then they're doing their job either on time or they're late with their job. Ironically, it's generating who's late to school, but okay, so on time versus late for both. All right, so we are told Rudy fails to get the list done 10% of the time. So it's late 10%, on time then 90%. And the other person, Fawn, is on time 92%. So that means this person's late 8%. With tree diagrams, I multiply my branches together. I get 0.27. 0.3 times 0.10 is going to be 0.03. And then 0.644 when I do 0.7 times 0.92, and then I have 0.08. I always then quickly sum this and make sure it adds to 1 so that I don't make any errors. Okay, now this is having us work backwards. Let's say that you're the principal and the tardy list is late. Okay, so where is it late? Could be this value or this value. What's the probability that it was Rudy who did it? Okay, so what's the probability that it was Rudy given that it was late is what we're asked to find. Beautiful thing is, this is like working through a tree diagram backwards. We don't have to like overthink this. Go to your formula sheet. That's the probability of the intersection, I'll use R for Rudy and late, given that you're late. What's that equal to? Well, the intersection of the two, Rudy and late, would be the 0.03 over probability of late would be add 0.03, and I just spotted an error. That 0.08, I never actually did the multiplication, did I? I got to do 0.7 times 0.08. That's got to be 0.056. And if I really had added to 1, like I said I should, I would have noticed that I made that error. And so I said it, but I didn't actually do it in this video. All right, and that shows how it can come back and bite you. So I've got it actually now, probability that they're late is 0.03 plus 0.056, which would be 0.0, excuse me, 0.086. All right, so I do that division and I get 0.3488 approximately. Okay, so this is a good review of your basic probability rules, and we hit independence 3 times.